using different sequencing rules, such as earliest due date versus shortest processing time, should generate different sequences, although not always. This particular scenario with the Middlebright job shop is a good example of that exception. Let's take a look. The table below contains information about 5 jobs waiting to be processed at stamping machine 307 at Middlebright job shop. Okay, so typical job shop sequencing problem. Here are the jobs, here how long they'll take, and here's when they're due. Now let's look at this question. Which of these 3 rules provides the best sequence in terms of average flow time? And 3 rules are named: earliest due date, critical ratio, and shortest processing time. Okay, so each of these 3 rules should generate a different sequence. Each sequence can be evaluated on average flow time, and the question is asking that which one has the best, which is to say the smallest average flow time. All right, so to answer this question, what we should do is generate the sequences, one for each rule, and then do the flow time calculations. 2 of them we can do quite quickly: earliest due date and shortest processing time. Let's just make some room here. Let's see, earliest due date. We want to stay organized here, because we're going to have 3 different rules and 3 different schedules going. Now first off, with earliest due date, we want to generate the sequence. Well, the sequence is created by, let me scoot this down a little bit where we can see the data. With earliest due date, the sequence is created simply by sorting on the due date, in which the smallest due date will be first. Oh, which I'm pointing to it actually. The smallest due date is E. It's due in an hour, so it would go to the front of the sequence. Fine. Then who's the next smallest? Okay, C. Then who's the next smallest? Meaning A. And then who's next? We're just sorting here, D. And then finally, the largest due date, the one that's farthest in the future, is B. That goes to the end of the sequence. All right, so we have the sequence. It's asking about flow time. So now I need to calculate the flow time of each one of these jobs in order to then calculate the average flow time. Okay, fine. The flow time of E, well, it's at the beginning, so I just check the processing time. It's 4 hours. Flow time is when a job will be finished. It will be finished in 4 hours. Now C has to wait for E to finish. So C has to wait those 4 hours, plus then I look up the processing time for C. It's 1 hour's worth of work. It will finish in 5 hours. A has to wait those 5 hours. A is 3 hours worth of work, so the flow time for A is 8 hours. It'll be done in 8 hours. D, 8 plus processing time of 2, 10. B, 10 plus, look up the processing time for B, 5, 15. Yes, the general rule is the flow time for a job is the flow time of the job before it plus the own job's processing time. Now, these are the flow times. The question is asking about the average flow time, so we need to just average these numbers. Average 4, 5, 8, 10, and 15. I did that. I get an average, just could note it down here, average of 0.4 hours. That's a little sloppy. That's 8.4. Okay, average of 8.4 hours. Fine. Now, it says critical ratio next. We're going to compare all of these. But what I'm tempted to do is let's just skip that for now and do shortest processing time. The reason is the shortest processing time is pretty fast as well. We'll save the more complicated one to be the third one. Now, I also want to be careful looking ahead in the problem and leave a nice workspace in here. Let's put shortest processing time right here. I'm just trying to leave somewhat of a margin in between them. You'll see why later. Okay, shortest processing time. First, generate the sequence. This time we're going to sort on the processing time itself. Who's the shortest job? Well, I'm looking at the data and I see that C is only 1 hour. C goes to the front of the sequence. Then I'm looking at the data and I see that D is only 2 hours, so it's next, and then A, and then E, and then B. This is the sequence. Oh, okay, now what are the flow times? Well, I'll make another column. Flow time. Let's see, C is 1 hour worth of work, so it'll be done in 1 hour. D has to wait for that hour, and D is 2 hours worth of work, so its flow time is 3. It will be done in 3 hours. A has to wait for those 3 hours, then we work on it. It's 3 hours worth of work, so it will be finished in 6 hours. E is 6 hours worth of work. E has to wait 6 hours. E is 4 hours worth of work, so its flow time is 10. And then B is 10 hours worth of work, plus B is, again, B has to wait for 10 hours. B is 5 hours worth of work. The flow time for the job called B is 15. What's the average? You just want to average 1, 3, 6, 10, and 15. I get 7 hours. Oh, all right. So far I can see right away that the flow time for shortest processing time is nicer than the flow time for earliest due date. We were asked to compare 3, so we aren't ready to answer the question yet because we do have to check critical ratio. But before we go on to critical ratio, I want to point something out. A good check of your math. Notice how we have different flow times in here. The flow time of the last job is 15 in both cases. That's a good check on your math. The flow time of the last job in any sequence, it's not just this problem, any sequence should be the sum of the duration data. If you go back up here and you add these numbers, they add up to 15, okay? That and that and that should always match. Oh, all right, now, we still need to answer this question, and this question also included critical ratio. Critical ratio is not hard to do, but it's a little bit more arithmetic than the other rules, which are really just sorting. Critical ratio is sorting as well, but what you want to sort the jobs on is their critical ratio, so you have to calculate that first. Now, what's critical ratio? Let's go back to the data. There's some room to work up here. First off, we have to remember that critical ratio is always time remaining divided by work remaining. Critical ratio is a score. It's a single number for a job, something that needs to be done. It is always calculated by some form of time remaining to work remaining. Now, in this particular simple setting, we say time remaining, work remaining. Well, you're actually looking at those numbers because the processing time is the work remaining. That's the work that needs to be done, and if we're putting together a sequence, no work's been done right now. Okay, that's work remaining. And if it's right now is 0 hours until due, that's the time that's remaining. Oh, so really, why don't I just add another column here, CR for critical ratio, time remaining to work remaining? Okay, this is the time remaining. For instance, for job A, 4 divided by work remaining, 3. The critical ratio for job A is 4/3. Let's see, for B, time remaining is 9, work remaining is 5. For C, time remaining is 3, work remaining is 1. Oh, so the critical ratio is 3. For D, time remaining is 6, work remaining is 2. So the critical ratio is also 3 for D. Anyway, for E, time remaining is 1, work remaining is 4, 1/4. Oh, all right, that's the critical ratio for each one of those jobs. We're trying to piece together a sequence. How do you piece together a sequence? You look for the smallest ratio. Smallest ratio should go first. Okay, so that means that down here, I could start up another worksheet, critical ratio, for instance. And I now know something about that sequence because I look here for the smallest number, and do you notice that the smallest number is that 1/4? Right, what does that indicate? E should go first. It belongs to E. For critical ratio, E would be at the front of the sequence. Oh, okay. Now, you might be thinking, oh, I see, and then you sort, and let's see who's the next smallest and who's the next smallest and the next smallest. No, actually, that is not the best way to use critical ratio. Critical ratio is always time remaining to work remaining. Notice we've made a decision. We've decided to do E first. Okay, we've made a commitment. So, glance at the data. E is 4 hours worth of work. Now we know what we're doing for the next 4 hours. But 4 hours from now, we're going to need to decide again who should be next. We should recalculate the critical ratio for the remaining jobs to update them to 4 hours later, because that's the next time we'll pick somebody to work on. Oh, all right, update them for 4 hours later. Yes, these numbers here refer to how many hours until due from right now. Now it's 4 hours later. Oh, which means in the numerator we should, essentially from where we are right now, should take away 4. Oh, yeah, because, think about this, critical ratio, column again, if this is due in 4 hours right now, 4 hours from now, it is due. Or 4 minus 4 is 0. There's still 3 hours worth of work. The critical ratio for job A goes to 0. Now, as opposed to, look at job B. Originally, if you're talking about right now, it's due in 9 hours. But if we're going to be busy working on E, that means 4 hours from now, there's only 5 hours remaining until it's due, time remaining, or 9 minus 4. Although it's still the same old 5 hours worth of work, now the critical ratio is 1 for job B. In the case of C, 4 hours from now, it will be 1 hour late. Or take this old numerator and subtract out 4, negative 1. It is still 1 hour worth of work, meaning now the critical ratio is negative 1. And then in the case of D, let's see, 6 minus 4 is 2. The critical ratio sinks to 2 divided by 2, or 1. Oh, now you have to update the ratios. Now we have updated ratios. And we want to look again for just who's the smallest. Well, the smallest is now this negative number. It belongs to C. Yes, it belongs to C. Great. C is next in the sequence. Okay, now what? Now update them again. Getting the sequence with critical ratio, right, is the hard work. Okay, we've determined the first two in the sequence. Now we need to determine the third one. Although, I want to point something out about interpreting critical ratios. If you're given a report that has critical ratios on it, if you see a number that's positive, but it is a fraction, like I'm pointing at this 1/4, that is a job that, as you're looking at the report, is not late. Right? In this original column, job E had a critical ratio of 1/4. Right now, job E is not late, because if you're talking about right now, it's due in an hour. If it's a fraction, though, that is a job that's not late, but it's going to be late. It's doomed to be late. And job E was always doomed to be late because it's due in an hour and we're told that it's 4 hours worth of work. It's gonna be late. If a job's ratio is negative, you're looking up the report, that is a job that's already late. And you can see that with the one we just selected, C. Okay, by the time we get around to selecting it 4 hours from now, it's already late, but we're putting it next in the sequence. Anyway, we need to finish this sequence. So, let's update again. Critical ratio again. Now we have scheduled C, right? We've done E, we've done C. We need to update these other three based on the fact that now it's 1 hour even later. It's 1 hour even later because now we're doing C, which means I subtract 1 hour, negative 1/3, 4/5, and then down here, 1/2. I subtract 1 hour from each of the remaining numerators. Again, I look for the smallest number. It's negative. It's this one right here. Oh, okay, so that means that that belongs to A. A goes next. Oh, now what? Now I need to do it again. I need to update again. I'm only trying to decide who goes next to last and who goes last, but I should do that based on critical ratio. Okay, now we have just committed to completing job A, which means now it's for the remaining ones 3 hours later. Take 3 from the denominator. Okay, critical ratio for D is now 1/5. And for, let's see, critical ratio here, take away 3 is a -2 divided by 2. Who's smallest? Now, this is smallest. This one belongs to D, right? This one belongs to D. Excuse me, this one belonged to B. This one belongs to D. So D goes next. Which means that now there's only one left over. That goes last. Well, then that would be B. That's how you do critical ratio. Okay? You do it once, you pick somebody, and then based on their completion time, you update everybody else, and then again you pick the smallest, and then you keep doing that. Oh, so finally you come up with a sorted sequence. Now you're thinking, we're not even done with this question. Now we have to calculate the flow times and then calculate the average flow time to just answer the question. Do you notice a coincidence? This is our work with earliest due date. That's our work with earliest processing time. Hard fought. We came up with the critical ratio sequence. It's exactly the same as earliest due date. Now, that's a coincidence. I mean, that doesn't always happen, but it happened in this case. So, at least that's a little bit of good news, right? Because I know exactly what the average flow time is. It's 8.4 hours. I already did that work. I don't need to calculate the flow times again. This is going to match that. Oh, okay, so finally, at long last, what did they ask? Which of these 3 has the best average flow time? The answer is shortest processing time, because it's 8.4 versus 7. You always want the smaller. Oh, all right, good. Now, this is not the only question associated with this problem. What's the next question? Which of these 3 rules provides the best sequence in terms of average tardiness? Oh, now we need to calculate the tardiness associated with each one of these sequences, and then calculate the average tardiness and make a comment on who has the best, which is to say the lowest. Oh, now we could generate the sequences again if you want, but I would prefer to take advantage of the work we've already done, because it's these same 3 sequences that are being asked about. It's just that now they're asking about tardiness. So I'm going to add a column. That's why I wanted to leave a space in here. You need flow time in order to calculate tardiness, because in the case of earliest due date, the flow time is 4. We'll finish in 4. In the case of E, I'm looking up the due date, and it is 1. The tardiness here then is 4 minus 1 equals 3. It's going to be 3 hours tardy. Okay, in the case of C, it will be finished in 5 hours. I'm looking up the due date. It's 3 hours. 5 minus 3, it will be 2 hours tardy. In the case of A, it will be done in 8 hours. A was promised in 4. Boy, we are not making anyone happy here. It will be 4 hours tardy. In the case of D, it will be done in 10. D was promised in 6. 10 minus 6 equals another 4 hours late. And in the case of B, it will be done in 15, but it was promised in 9. So it will be 6 hours late. We want to know the average tardiness. Actually, it's asking on the next page. Might as well write it there. Average tardiness for earliest due date. Well, you would just want to average the 3, the 2, the 4, and the 6. So that's all what? Divided by 5? I get an average tardiness of 3.8. That this comes out to 3.8? Oh, okay, now that's only one of the three. What about shortest processing time? Well, again, there's some room over here. We might as well add it over here. Tardiness. Tardiness. Okay, C will be done in 1 hour. C, I'm checking the data was promised in 3 hours. C will be done early in this case, so the tardiness is 0. D will be finished in 3 hours. I'm checking the promised time. It was promised in 6. It'll be done early. The tardiness is 0. A will be finished in 6 hours. A was promised in 4. All right, so there we're running behind. 6 minus 4, 2 hours tardy. E will be finished in 10 hours. E was promised in, oh, that's not good. E was promised in 1 hour, so 10 minus 1 is 9. And then B will be done in 15 hours, and B was promised in 9 hours, so it is 6 hours behind, or 6 hours tardy. This is what you want to average for here. Shortest processing time, 0 plus 0 plus 2 plus 9 plus 6 divided by 5. We're just averaging. And I got 3 point something. What did I get? Oh, 3.4. 3.4 hours. Oh, right. And then I'm just going to write CR, critical ratio. Except that, yay. Critical ratio has the same sequence as earliest due date, so it will have the same average tardiness as well. So I don't have to do any calculations. That's going to be 3.8 hours because these two things are actually the same sequence. Who has the best? Notice that in this case it is shortest processing time. That won again. Okay, so that answers that question. Now, last question associated with the scenario. In each of the three sequences, okay, each of these three, right, when will job C be finished? Oh, I think we can answer that because we've already done those calculations. That is also another way to say that the flow time of job C, we've got that work. Because, for instance, in earliest due date versus shortest processing time versus, just going to write CR for critical ratio, we'll go find C. Okay, in the case of C, earliest due date, flow time is 5. It will be finished in 5 hours. That's what that means. In the case of shortest processing time, find C. Oh, in the case of shortest processing time, we put C at the front of the sequence, so it'll be done in an hour. Okay. And then, wait a minute, critical ratio generated the same sequence as earliest due date, so C is finished at the same time. It is the same schedule. It's 5 hours. So, there's your answer concerning job C.